This is Physics 2212, Lab 4 Circuits. So the purpose of the lab is to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional currents and potential differences in the currents, or the circuits, examine the behavior of ohmic resistors and capacitors. So preview the result is that the experimental RC is 5.99 ohms, which is really close to the actual RC given like a small degree of error. So some fundamental principles is the loop rule, where the total potential differences in the loop must equal 0. The node rule, you have Ohm's law over here. You have the potential difference of the capacitor, and you have the capacitance, which is of course of the capacitor. And this is how we're going to calculate RC, which you'll see in a graph later on in the slideshow. So for the experiment, the first part of the experiment is a series circuit. So the system is a circuit, the surrounding is everything else. The predicted current is going to be 0.0204, and as you can see in the experimental current, it's 0.02, which is really close to each other. The ammeters, if you reverse the ammeters, then you're still going to get a current of 0.02 amps, and that's because the current just does not change. If you replace the ammeter with a voltmeter, your voltage will be 3 volts. And it's an open circuit and there's no current flowing through the voltmeter. So the potential difference around the circuit, we're going to do it from each level. And as you can see, that B, C, D, E, F, all the way to A, all over here, there's going to be no voltage. So you can see this in this graph right over here. And the sum of potential differences is going to be a loop rule because it's a closed circuit. So the total of all of the voltages, the potential differences, is going to be equal to 0. So why doesn't the ammeter reading change when you attach the voltmeter? So that's because there's a high resistance from the voltmeter, and that prevents the flow of the current. So what happens to the current through the ammeter if the voltmeter is replaced with an ammeter in parallel to the 100 ohm resistor? The current actually increases from 0.02 to 0.06. And since the resistance decreases, the current increases at the end of the equation, V equals IR. So the 47 ohm resistor is going to equal 48 ohms. The R of the 100 ohm resistor is going to be 102 ohms. And then for the wire and the ammeter, it's going to be 0, as seen in these calculations right over here. So what happens to the bulb when it's connected to the battery? Well, the bulb is very light, but over time it's going to dim down. So, but when it's connected to a capacitor, it's still going to be very bright, but once again, it is going to dim down, same as the bulb when it's connected to the battery. So for both scenarios, the current is as greatest at 9 volts and decreases over time until it reaches 0 volts. And that was experimentally calculated through doing it with a 10 bulb and a 20 bulb. So for a 10 bulb, the charge and the discharge is approximately the same. The discharge is a tiny bit larger, and that's the same for the 20 bulb. So as you can see, the 20 ohm bulb takes longer to charge and discharge than a shorter or smaller ohm bulb. So here you can see our experimental data. So this is just the voltage versus the time. This was calculated over a period of 20 seconds with 0.5 intervals, and the voltage was calculated from 9 all the way to 0. So that can be seen here as it's an exponential graph. And when you take the ln of that to do linearization, you get all this data over here, and your experimental RC is going to be the slope equals -1 over RC. So that's how we got 0.599 seconds. And then the expected RC is going to be 6 seconds. That's calculated by the ohms times 0.2. The possible sources of error could be rounding or measuring or just some external forces that could have caused anything. So what if you were doing this in real life and you use an actual ammeter instead of an ideal simulated one? What's the difference and how would that affect the circuits? So the real ammeters have resistance, so the measured current would be lower. So what if you were doing this lab in real life and you used a real battery and a real capacitor and no resistor in the circuit? So a full charge would be achieved immediately in the ideal model. However, it would take some time for it to be fully charged in real life because there is resistance in each component, and that can't be seen in this experimental model, but in real life it can be seen.